in previous videos, we talked about the kinematics of frontogenesis and whether or not it can produce a front in a reasonable amount of time. We also investigated whether QG dynamics could get us a front in a reasonable amount of time. And neither one could. So we must pivot and look at some extra parts to our momentum equations to come up with something that will work and will give us frontogenesis in a reasonable amount of time, with also representing fronts in the appropriate way, i.e. tilting towards cold air, only regions of static stability, and only cyclonic wind shifts associated with our fronts. And so before we begin figuring out what additions we can use to our equations, let's go ahead and first recall what our QG momentum equations look like. And so let's recall that our QG equations, dVg dt plus Vg dot del Vg, these all being vectors, so we are doing two equations here in one, equals minus F times K hat cross Vg plus Vag, our ageostrophic wind, minus del P phi. And so with our equation here, we can see a couple of different things. We've got our time rate of change of our geostrophic wind vector. We've got the advection of geostrophic wind by the geostrophic wind. We've got our Coriolis term here, where the Coriolis term is with the total wind, the only place within our QG framework that we have the total wind, and our pressure gradient force, or height gradient force, in this case, on a pressure surface. And so this is our QG momentum equations. If we were just considering pure geostrophy, we would only have our height gradients and our geostrophic Coriolis parameter. But even in this QG framework, we noted that frontogenesis takes too long and has other undesirable characteristics, such as static instability in the vertical in some locations, cyclonic and anticyclonic rotation. And so these are not ideal setups. And so we need to add some more pieces back in here into our equation to come up with a better approximation that will allow us to get frontogenesis in a more reasonable amount of time. To do so, we're going to need something called the geostrophic momentum approximation. And our geostrophic momentum approximation is going to add in two more otherwise neglected elements from our QG equations. Specifically, we're going to want to add back in our elements of the advection of geostrophic wind by the ageostrophic wind and the vertical advection of geostrophic momentum. And so, really with our full equations of motion, remember we have the total wind everywhere. And so by making these various approximations, we're simplifying the process. And for various scales of motion, for example, synoptic scale motion, things like QG dynamics work well. But this idea of fronts that run at both the mesoscale and the synoptic scale, we need to add in a couple of these elements to get the proper secondary or ageostrophic circulations associated with them. And so the question is then, what does this look like in terms of our geostrophic momentum approximation equation? Here we can add in our dVg dt. This is an unchanged term. Plus now here we're going to add in this first element, this idea of the advection of the geostrophic wind by the ageostrophic wind. And so now we're going to have not only Vg, but plus Vag dot del Vg. So now our advection term here includes the total wind and not just the geostrophic wind. Additionally, we're going to add our second piece here, the advection of the vertical advection of geostrophic momentum here with our omega dvg dp term equals, and then our right-hand side is going to be the same as before, minus f k hat cross vg plus vag minus del p phi. And so if we look at both of these equations here, our geostrophic equation up here at the top and our geostrophic momentum equation here at the bottom, we see that we have these additional terms. Our additional terms here is this VAG dot del VG term. That's this ageostrophic, the advection of geostrophic wind by the ageostrophic wind. And our vertical advection of geostrophic momentum term. By adding these two terms in, we can use this geostrophic momentum approximation in a new semi-geostrophic theory. So use the geostrophic momentum approximation to develop semi-geostrophic theory. And what semi-geostrophic theory is in shorthand here, we're not going to go into this in detail, but we can use these geostrophic momentum approximations, put them into something called the geostrophic space, so that then we simplify the equations again with these extra complications to then do and calculate things related to frontogenesis. And when we do so, we can see what this semi-geostrophic theory can do to represent our fronts and see if we can get it in the correct time scales and with the correct spatial orientations. And so another equation that we can think of that we're not going to write down here that would explain these vertical circulations is something called the Sawyer-Eliason equation. The Sawyer-Eliason equation is going to be one that describes these secondary ageostrophic circulations. And I encourage you to read the textbook by Lackman in the frontogenesis chapter to read more about the development of the Sawyer-Eliason equations and what they mean. What we're going to do, though, is look at if we were to use these geostrophic momentum approximations, putting them into geostrophic space to then generate this semi-geostrophic theory, and where this geostrophic space is where air parcels flow along with the geostrophic wind. And so essentially we're creating these geostrophic coordinates. Again, this is not too complicated, but in essence you can think of using these equations and putting them into a framework that simplifies them a little bit to solve for our vertical circulations in a simplified space to then bring it back into our physical space at the end. When we do so, and if this is done, we can then develop cross-sections of what that looks like. And so initially here, this top figure is going to be our QG framework, our plain old QG framework that we looked at previously. And we see at our fronts, we get this generation of a secondary circulation as indicated by the arrows here. And this would be a direct circulation in this case. And we see we get our infinitesimal points, we got our vertical instability going on here, and not all of our isentropes are tilted towards our cold air. Now if we look at this same cross-section, but using semi-geostrophic theory, which uses our geostrophic momentum approximation, we now get our circulations to happen in a way that tilts all of our isentropes towards our cold air, has areas of only static stability, and so we see here our region of static stability, right? Regions where these isentropes are closer together, and that everything tilts appropriately towards that cold air, and our circulation tilts as well. And so it turns out by adding in just those two pieces, the advection of the geostrophic wind by the ageostrophic wind, and the vertical advection of geostrophic momentum, we have now added the necessary pieces to more fully explain these secondary ageostrophic circulations related to fronts. It does so if we compute these things numerically, is fast enough that it compares with OBS. We get the appropriate ageostrophic circulations and convergence that accelerate to form the front or increase the magnitude of our gradient in potential temperature. The fronts tilt with height towards the cold air while remaining statically stable, and we only have regions of large cyclonic vorticity along frontal boundaries. And so this semi-geostrophic frontogenesis, using the geostrophic momentum approximation, are much more representative of actual observations. And it's all through accounting for more elements of the ageostrophic wind, specifically that advection of the geostrophic wind by the ageostrophic wind and the vertical advection of momentum. Now that we've uncovered a little bit about the theory behind these things, in a future video, we're going to go through a realistic how do we get from just a temperature gradient with initial convergence towards this full tilted ageostrophic secondary circulation associated with our fronts and our factors factoring into the semi-geostrophic theory. Thanks for watching.